So, today we'll talk about improved circular k-mismatch sketches. My name is Shai Golan, and this is a joint work with Tomasz Kociumaka, Cviko Pelowicz, Eli Porat, and Przemek Kuznański. So, first of all, let's recall the definition of Hamming distance. So, the Hamming distance of two strings of the same length n is the number of aligned mismatches between the two strings. In this example, the Hamming distance between the strings is 4. In the paper, we consider strings in circular manner. So instead of writing the string in a line, let's write it in a circle. Then, the definition of a cyclic shift of the string is the concatenation of some suffix of the string, let's say of length m, with the complementary prefix. The circular Hamming distance of two strings S1 and S2 and the specific cyclic shift m is just the Hamming distance between the string S1 and the mth cyclic shift of S2. In this example, the Hamming distance is 10. The shift distance of two strings is defined as the minimum Hamming distance among all the possible cyclic shifts of the strings. In this example, this is the minimum Hamming distance, it's 3, and therefore it's the shift distance between the two strings. In the sketching model, we want to store small representation of a string, and in our problem, the goal is to compute small representation of strings such that if we are given the sketch of S1 and the sketch of S2 and some shift value m, then there is a decoder that can report the Hamming distance of S1 and the mth cyclic shift of S2, assuming that this Hamming distance is at most k, and if the Hamming distance is larger than k, it's just enough to report that this is the case. We consider such sketches both in the exact manner as we described now and in the manner of 1 plus minus epsilon approximation, where the result that the decoder should output could be just approximation of the Hamming distance. So the state-of-the-art result so far for this problem in the exact sketch, in the exact manner, is by Andoni et al. From stock 13, where they introduce sketches of size O tilde of d of n plus k, where d of n is the number of divisors of n. While for many numbers this function dn is not too large, in the worst case, d of n could be n to the theta of 1 over log n. Moreover, Andoni et al. Proved that there exists a lower bound of omega of dn space for linear sketches up to polygons. We improve upon the result by introducing sketches which are not linear, and our sketches space is just O tilde of k. In the approximation regime, the state-of-the-art result is by Krochmore and McGregor from approx 11, where they introduce sketches of size epsilon to the minus 2 square root n, and we improve the result to O tilde of minimum between epsilon to the minus 1.5 square root n, which improves the epsilon dependency, and epsilon to the minus 2 square root k, which means that if we are just interested in strings, in the Hamming distance of strings that are close to each other, then the dependency is on the boundary k, which we define instead of n, which is the length of the strings. Now I want to discuss a little bit about the relation between our problem and the text-to-pattern Hamming distances problem. So in the text-to-pattern Hamming distances problem, we are given text t of length n and a pattern p of length m, and the goal is to compute the Hamming distance between the pattern and every substring of the text of the same length as the pattern, length m. For example, here the Hamming distance between the pattern and the first substring of the text of length m is 2, the Hamming distance between the pattern and the second substring of the text is 4, and so on and so forth. The goal is to compute the Hamming distances for all the substring of the text. And there is a well-known reduction from instances of circular Hamming distance to instances of text-to-pattern Hamming distance. So the reduction goes as follows: just set the pattern to be one of the strings, S1, and set the text to be the second string concatenated to itself. And it is well known that the Hamming distance between S1 and any cyclic shift of S2 is exactly the same as the Hamming distance between the pattern, which is S1, and the ith substring of S2 of length n. And an interesting fact is that in the offline setting, there is no separation known between the two problems, while in the sketching model, in our solution and also in previous solutions, the exact circular sketches uses much less space than the sketches for pattern matching. Even if we just interested in k equals 0, which means exact matches of the pattern in the text, or the two strings to one to the other in some cyclic shifts. Another interesting relation between the problems is that if we consider the space for streaming algorithm, which means that the pattern is given in advance and the text arrives one character at a time, and we just allow to store a small amount of space, then the state-of-the-art algorithm for the streaming model, of course, we consider the k-Mismatch variant, is exactly the same as our new sketches up to polylogs. So the state-of-the-art for exact computation is by Chumaka et al. From Soda 18. This streaming algorithm uses O tilde of k space, exactly like our circular k-Mismatch sketch, and for the 1 plus minus epsilon approximation streaming k-Mismatch algorithm, the state-of-the-art is by Chan et al. From last stock, which achieve the same space usage as our circular sketches. Now I want to give algorithmic overview on the algorithm, on the paper and the algorithm. So the main tool we define in the paper is the selection function. We will discuss about it in a few minutes. Then we show how to use this selection function in order to introduce 1 plus minus epsilon approximation sketches and exact sketches. And of course, we discuss how to construct such functions, and there are two cases which we cover in the paper. And there are some kinds of strings that we need to solve using a different approach, because the approach of selection function will not work for them. And we will discuss about this issue also in a few minutes. So this is the parts of the algorithm. And in this talk, I will focus on just on several parts, and the other parts are, of course, in the paper. So first of all, let's discuss about the selection function. So the selection function is defined as a randomized function from strings of length n to positions, indices in the range 1 to n. So it's to subsets of the range 1 to n. Let's, for example, maybe this is the position the function select for this specific string. And we want this function to have three properties. The first property is that the selection is preserved by rotations, which means that if, for example, in this string, the function select position 2, 5, 7, 8, 7, 9, 10, sorry, then if we consider cyclic shift of this string, we consider this shift rotated by 2 positions, then the positions selected by the functions are also rotated by 2 positions, and instead of position number 2, we now take position number 4. Instead of position number 5, we take position number 7, and so on and so forth. The second property that we want to have is that the the size, the number of positions we select for string is not too large, is O tilde of k with high probability. And the last property, the third property, is that if the Hamming distance of two strings is small, then we want that the intersection of the position selected for the two strings is at least k. The problem with, we have problem when we want to find such selection function, is that there are strings that we can be sure that there is no such selection function. So, for example, if the string composed of repetitions on the same character a, then let's consider the first index. If we take the first index, assuming that the selection function select is index number 1, then by the first property of the function that the selection is preserved by rotations, it must be the case that for any cyclic shift, we also take the corresponding position. However, since this string is the same after every number of rotations, it must be the case that we take all of them. And then we don't have the second property. We contradict the second property that requires that the number of position will be small. However, the option for not taking none of the position, it's also not fine because it contradicts the last property, the third property that requires that the size of the set will be large and even the intersection of this set with another set will be large. Therefore, for such strings, there is no selection function, and we generalize this problem, this class of strings, and call them high powers. And as we said before, we don't treat them with selection function, but with different approach. For the rest of the talk, let's ignore these strings and just consider strings which are not high powers and are not close to high powers. Now, I want to discuss about how we use a selection function, assuming that we have a selection function, and at the end, we will discuss how to construct them. So we will we will show the approximate sketch, and of course there is also an exact sketch. So as a background, let's describe note that there is approximate sketch for regular strings, non-circular strings. So if we are given S1 and S2, then there is a sketching scheme such that one can maintain just sketch of S1 and sketch of S2. The size of each sketch is O tilde of epsilon to the -2, and given sketches of two strings, there is a decoder that computes the Hamming distance of S1 and S2 with, not compute, but approximate this Hamming distance with 1 plus minus epsilon factor, approximation factor. And we will use these sketches as black box. Now, when we want to construct 1 plus minus epsilon approximation sketches for circular strings, let's start with first attempt that we later improve. So first of all, when we are given, while we sketch some string, first of all compute the selected positions for this string. Then, for every position that is selected for this string, let's compute the sketch, the regular sketch of the string in the specific cyclic shift that corresponding to this position I. So for example, for this position, we have this alignment. And for the next position, we have that string, and we will maintain O tilde of epsilon to the -2 space for the regular sketches of this regular sketch of this string, and we will do it for any selected position by the selection function. While we are given the sketches, the circular sketches of two strings, S1 and S2, and some specific shift M, we first compute the sketch of the cyclic shift of S2. And notice that it just requires us to rotate the positions, and it's easy to compute. Now, after we compute the sketch of the cyclic shift of S2, let's check if the intersection of the positions that were selected is smaller than k. If it is smaller than k, then by the third property, with high probability, the Hamming distance of the two strings is large, and we just report that this is the case. Otherwise, the intersection is large, and let's take one position in the intersection. Let's say this position I is in both sketches, and let's use the pre-computed sketches of regular string started at this position in S1 and in S2, and use this to approximate the Hamming distance. Notice that the size of these sketches is O tilde of epsilon to the minus 2k, and we want to improve it to epsilon to the minus 2 times square root k. Thus, the improvement goes as follows. We, instead of computing the sketch of regular string for any position that is selected, we do it for any position with probability about 1 over k, square root of 1 over k, or more accurately, 2 times square root ln n over k. Then for most of positions, we don't compute it at all, and we just focus on several positions. And for them, we compute the regular sketches. Now, if we are given two strings, S1 and S2, and in any cyclic shift, the probability of position that is in both, that is selected for both strings, the probability that this index will survive in both sketches is the multiplication of the probability it will survive in one sketch. And therefore, it's 4 ln n over k. And then, if the size of the intersection is large, is at least k, then with high probability, at least one position will survive. How we use it? Then during the decoding, we first of all, of course, compute the shift as before. And after we compute the shift, we check what is the size of the intersection. If the intersection is empty, then with high probability, the original Hamming distance is large. And if the intersection is not empty, then there is index I, at least one, and we use this index and the sketches that we already computed for this index in S1 and in the cyclic shift of S2 to approximate the Hamming distance of S1 and the nth cyclic shift of S2. And now the size of these sketches is O tilde of epsilon to the minus 2 times square root k. That's what we want. Finally, I want to discuss a little bit about how we construct such selection function. So we use hash function. First of all, let's define L, length, to be something around n over k, n over ck for some parameter c, which is constant. And now for any position I, we consider ui to be, we define ui to be the string, the substring of S of length I starting at, or of length L starting at position I. And of course, we consider S as circular, then if I is near the end, then the substring go also for the beginning after the end. And now we use hash function from strings of length L to 0 and 1, such that the probability of any string to achieve 1, to get 1 in the function h is about k over n. It's 4k ln n over n. And we say that string u is active if it has one value due to h. And now the construction is straightforward. We take for any position I, we take I into the selected set, if and only if ui is active. And we need to prove that this selection function has the three desired property. As the first property is obvious, the selection is preserved by rotations because this decision whether we take position I depends on the string, not on the index. And therefore, if we rotate the string, we rotate also the decision, the index that we take. And for the second and third properties, we discuss in a moment. So by linearity of expectation, the expected size of fs, the expected number of positions we take, is O tilde of k as required. However, we want it to be not just in expectation, but also with high probability. And the variance here might be too large, which is a problem. Thus, instead of consider all strings UI, the problem could be also could be only if there is some string that could appear too many times, and therefore it affects the size of the selected position set in too many times. And therefore, we consider just strings UI that cannot appear too many times. And we do it by using the periodicity of UI. And by Chernoff-Hofding bound, if let's assume now that all the positions for all the i's UIs is not periodic, then by Chernoff-Hofding bound, the size of the selected set is theta of k ln n with high probability. And for positions where UI is periodic, we use a different approach that we will not talk today. For the last property, the third property, notice that if we are given two strings, S1 and S2, that they are close to each other, they have distance at most k, then we can define UI to be the substring of S1 starting at position I of length L, and VI to be the corresponding substrings at position I in S2. And now notice that if UI equals to VI, then either UI and VI are active and we take I for both sketches, or for both for the selection function of both strings, or it is not active and then we will not take it for both strings. And therefore, every mismatch affects just the positions I where the mismatch is in the range of length L starting at position I, and therefore every mismatch affects at most L positions. But if we consider positions that do not contain any mismatch, then there is no effect and UI equals to VI. And in total, at most k times L, because we assume that S1 and S2 has distance of at most k, have at most k mismatches, then at most n over c positions have different UI and VI. And in particular, if we take large enough c, then most of the positions have UI equals to VI, and therefore by the Chernoff-Hofding bound from the previous property, assuming again for the sake of simplicity now that most of the positions are not periodic, then we know that the intersection of the position selected for S1 and the position selected for S2 is at least k. And by this, we prove also the last property. And of course, the parts that we don't talk about them today are appear in the paper. And that's it. Thank you very much.